Alright, so let's do some lecture 11, and we're gonna deal with some chemical equilibrium, and actually we're gonna derive the equilibrium constant or the reaction quotient from the chemical potential. And this is probably the most important lecture up to this point. So make sure that you understand this one. It's going to be quite complicated. We don't have any calculus on these things, but algebra is quite tedious. So I hope you get this. In general chemistry, if we have a reaction like this, then you can actually get the reaction quotient look like this, or the equilibrium constant look like this, right? And this is the time to actually make sure that equation right here is actually correct. So before I actually do these things, I want to actually clarify something here. If you actually have these things right here, right? The concentration to the power of 2, the concentration to the power of 3, right? Then what's the dimension here? You might think that each concentration is actually like a mole per liter or something, right? And then mole per liter to the power of 2 or power of 3 or power of 3. That is really not the case here. All of these things are actually pure numbers. What it means is that it looks like the concentration here, but in actuality, it's actually the concentration divided by a standard concentration, which is 1 molar. So this is really a pure number here. Let me just try to write out the unit here. For example, if I'm actually looking at the concentration of A to be the 2 molar, right? Then the number of mole divided by liter, right? That's the unit for this guy right here. But what's the number of what's the unit for this guy right here? That's number of mole divided by liter divided by number of mole per liter. This is just a 1. This means it's a 1 molar of whatever the things it is. So it's unitless. The whole thing is just going to cancel, right? And then this is just a number here for each one of these. And if you recall from the general chemistry, we can actually do these things for the partial pressure, for the gas phase stuff. That's also a unitless quantities. So maybe you may be thinking about ATM squared or something, but that's not really the case here. It's ATM divided by ATM, 1 ATM. So it's a completely unitless numbers. So you gotta keep that things in mind. Alright, so let's start out with the reaction quotient in gas phase. So we are trying to look for the Q in gas phase. Okay? So consider the reaction, this one right here, right? And this is the reactant before the reaction, this is the product, which is after the reaction, you get this one, right? If you recall from the lecture 8 that we did this scalar multiplier to actually get these things right here, right? So G, this is not the difference, it's Gibbs free energies is equal to chemical potential multiplied by the number of mole of that, right? And then if you have two of those, two different chemicals, then you have chemical potential of the second species multiplied by the number of mole of the second species, right? So the delta, not delta G, it's G for the reactant is this guy, right? You have A mole of A, B mole of B, so right? That's what you have right here. And for the G product, it's given by this guy right here, right? Because you have C mod of C, D mod of D, right? So that's what you get here. So the delta G, this minus that, is equal to this one, right? But in the gas phase, every chemical potential can be written in terms of this guy right here, right? That's also coming from the lecture 8 here. So we're going to substitute each one of these guys here. When you do, you have a front term, and then you have the rest of the stuff here. And if you do a little bit of algebras with the natural log, then you actually get these things right here. That's this part right here, and then this portion right here. If you have some multiple stuff, then that's going to be the power here. And then each one of these guys, if you sum it, then it's a multiplication. If you minus it, then it's a negative. So let me just try to fix something that I found a mistake here. Okay, so that's done. Alright, then once you've done this, then you actually get this Q is equal to this guy, and then that's equal to that. And that one right there is literally what we have for the gas phase reaction quotient. Hopefully that wasn't too difficult, because the next one is going to be like a little bit more difficult. Gas phase stuff is simple. The liquid phase is, as I look through the internet, there is interestingly whole bunch of different way of doing it, but I think I like mine the best. So let's go with my stuff. So again, that we're going to consider the reaction quotient Q in liquid phase. So this is going to be the concentration stuff, right? So starting out with the same formula right here, you have this reactant gives free energies, and then product free energies, right? And then delta G, you can actually subtract this this guy from that one, right? So that's the delta G. And then also the here is the thing that's like super complicated, but bear with me, okay? The chemical potential of the liquid is equal to the chemical potential of the pure liquid plus its mole fraction, right? That's what we have here. This is the chemical potential of the mixture, right? Mixture solution is equal to the chemical potential of the pure liquid plus RT log of the mole fraction, right? So if I actually use this one right here, and then apply it to actually make the chemical potential of A in 1 molar stuff, then you actually get the this part no change, but that portion right here, right? The mole fraction. For example, like if I actually use take water as a solvent, right? Then 1 liter of water have a 51 mole of water. Then the mole fraction is going to be 1/56, right? Yeah, close to 1/55. So approximately speaking. So this guy right here eventually becomes something look like this. Alright? And then if I actually compute the mole fraction of A right here, right? In the reaction system look like this, right? Now that we're talking about this system right here, it has the whole bunch of stuff in there, right? Then that mole fraction of A may actually look like this, right? Because it's like so many stuff is in there, right? But approximately that these things right here is dominated by 55 anyway, so it's you can actually write it something like this. Okay. Then the mole fraction, not mole fraction, the chemical potential of the mixture liquid solution is equal to chemical potential of the pure liquid of that kind plus RT log of this guy, right? That's the mole fraction, approximately speaking. And that's equal to no change here, but that one actually changes, right? Changes into the two part. It's a multiplication, right? So you can actually separate into the A times 1 over 55. So you can actually separate these guys. And then take a look at the first two term right here. That first two term is actually this guy, right? That's coming from this, right? So once you do that, let's go back to this minus that, right? Then you get this portion right here plus RT log of this things right here. This is not a fraction anymore, it's just a number of mole in 1 liters, right? Now wait, what's the number of mole in 1 liter? It's the same as the concentration, right? The number wise. And we don't really care about the what goes in here in the unit wise, because each one of those guys are unitless. As long as number is same, we don't care, right? So that little tiny c right here, that's the number of mole in 1 liter, right? That's actually equal to this one, right? Number wise, right? And you can actually repeat the same stuff, you actually get this one right here. And going back to the ones that we swallow, yeah, it's just the numbers, and then we just hide these the unit cancellation stuff. Then you can actually write the Q as this guy right here. And that one right there is a reaction quotient inside of the solutions. I apologize this one, but there are so many things that I wanted to actually clarify. And many of the textbook that I saw, there are some issues with it, that because that sometimes that you have these things to be the standard, and the inside of the liquid, the standard is actually defined as one molar solutions, right? So I just wanted to adjust all of those things into this form right here. Alright, that's good. Let's do the next slide. So what happens that if you are at the equilibrium? At the equilibrium, the delta G is equal to 0, right? So delta G is equal to 0. So delta G can be substituted to 0, and that's equal to this plus that, right? And in this time, that Q is substituted by K, right? And then bring these things over there, then you actually get this formula right here. And that formula, by the way, if you divide both sides by negative RT and then take a exponential, then you can actually get this formula. It's probably more familiar form. And either way that you can actually use either one of these to actually solve some problems. I think that's probably good enough for this one. One thing to note here is that if you actually have a K that's much bigger than 1, then obviously the product are dominant. And if it's much less than 1, then reactants are going to be the dominant species at the equilibrium. Alright, then what's the relationship between Kc and Kp? So the Kc right here is in a liquid, that's a liquid, and then that one right there is the gas, right? So let's start out with this expression right here that we just derived, and then using the PB code nRT, then rearrange that to get this one right here. But the first one of these guys is just a concentration, right? So the concentration can be replaced by this formula here. So we're going to replace everything that's inside of here with that guy. Then try to cancel out the try to actually take these things out of the stuff, and then instead that we are going to put P in that place, then you can actually get that expression multiplied by these things right here, and that's literally the conversion unit going from the Kc to Kp. So that portion right here is Kp, right? That's in a gas phase. So the gas phase equilibrium constant, and that's the liquid phase, the solution phase equilibrium constant, right? Those are related by this formula right here. And we actually covered these things in the general chemistry, but we really didn't derive it, but now you know. And I think that's pretty much all there is to it for this particular lecture.